On this page, we are going to talk about cyclic quadrilaterals. A cyclic quadrilateral is a quadrilateral whose vertices all lie on a single circle. That sounds like an amazing, impressive vocab word that you're probably going to know for some sort of an assessment. So highlight it. Next, habits of mind, right? We got to think like a mathematician. So in thinking like a mathematician, we're going to look for and make use of structure. We're going to look for and express regularity in repeated reasoning. And then last of all, this is directly related to the learning goal. We're going to understand that the vertices of cyclic quadrilaterals lie on the same circle. We're 100% emphasizing that goal from this lesson. Page 227. You're probably going to need a protractor to finish it out. You're going to need some paper, pencil, patty paper. And then we're going to also need to flip back a couple of pages to answer some of these questions. Let's start with number 1. Identify any cyclic quadrilaterals you drew on your piece of patty paper. Remember, the piece of patty paper, that's how you were keeping track of your notes to use them throughout the way. We're going to flip back to the page when we created them. So let's flip back through. I'm going to start on page 216 because this is when we were forming quadrilaterals using a circle. And on page 216, we actually created a square. A square is a specific type of cyclic quadrilateral. All of the vertices, those are the angles, the corners, all of the corners, vertices, are on the edge of one circle. So squares, add that to the list. Then on the next page, page 218, we created a rectangle. And notice it's one circle, and then the corners of the rectangle are all on the edge of one single circle. So this is also a cyclic quadrilateral. Cyclic, cycle, bicycle, circles. It's all connected, man. On the next one, page 219, 2 circles were needed to create that diamond, that rhombus. So, nope, not that one, or the parallelogram. 2 circles were needed on page 220, were needed to create the rhombus that's there. Page 221, 2 circles are needed to create the kite. Not looking good, guys. And then a trapezoid, same thing. So there's only 2 types of cyclic quadrilaterals that we need to know about. Squares, that was page 216, and rectangles, page 217, because they were created with just one circle. Okay, what is the sum of the measures of the opposite angles in the cyclic quadrilaterals that you identified? So let's flip back to page 216. And in flipping back to there, we have a square, so opposite angles, right? Opposite angles. Well, in a square, it's 90 and 90, so 90 plus 90 is 180. QR, those are opposite vertices, and the angles at Q and R are 90 and 90, so that's also 180. That should kind of be true for rectangles as well, right? In a rectangle, opposite angles are 90 plus 90. And in the other diagonal, those angles at Q and at R are also 90 plus 90, which is 180. So it seems like the pattern, a conjecture, if you will, is that the sum of the measures of the opposite angles is 180 degrees. That's really what it looks like, all right? I'm just going to leave it. There's more that I could write down there, but I'm going to leave right that one. Let's go to number 3. In question 3, consider the quadrilateral MATH. 4 letters that spell a word. Inscribed in the circle O. So we're going to use a protractor to determine the measure of each interior angle. So that would be, we can get to there if we just draw these lines longer. So I'm going to draw that line longer. I need them to be drawn longer because my protractor is much bigger than the shape. And this is the technique or trick to make the protractor useful. I wouldn't recommend getting something smaller too, because the bigger the protractor is, the more accurate you can be. All right, let's measure angle M. The measure of angle M is protractor, put the circle on M, line it up, carefully lining it up, making sure it looks like it's at 100. And the way that they designed this question, yeah, we want some nice numbers. The measure of angle M is 100 degrees. Let's go to the measure of angle A. Okay, center the protractor on A. I'm going to turn it this way so that I can actually line it up specifically. And then measuring it, kind of checking my line out here, 10, 20, 30, 40, 50, 60, 61, 62. The measure of angle A is 62 degrees. The measure of angle T, so that's up here. The measure of angle T, center up the T, line up the black line with the arrow, and then it looks like it's about 80 degrees. And then the measure of angle H. So that's down here. The measure of angle H. Oh, you know what? Angle A, I made this mistake, and I want to see that you probably make this mistake too. Nah, you're better than that. This is an angle that's bigger than the corner of a piece of paper. It's more spread out. So when I read the protractor, I need to be aware that there is a small number and a big number that together add to 180. Add to 180, add to 180. So it's not 62 degrees because that's a number that's smaller than 90. But that angle's definitely bigger than the corner of a piece of paper, which means the angle A is bigger than 90 degrees. So I got to choose the other value. I got to choose the number that's across from. So measuring again, just to be very accurate, 110, 120, using the bigger numbers, 110, 115, 116, 117, 118. And then angle H is an angle that's smaller than a 90-degree corner, which means I need to choose the smaller of the numbers, which means I need to choose 62 degrees right there. All right. Let's determine the sum or the measure of each sum. That's next part in this section. So the measure of each sum, angle M plus angle T. So I'm going to add the two numbers. I'm going to add 100 plus 80. You can do the rest. I'm going to add A. Measure of angle A is 118. By the way, you do this part. Okay. The measure of angle A is 118, and the measure of angle H is 62. Add them together. What do you get? You do that part. Let's make a conjecture about the measures of opposite angles in a cyclic quadrilateral. I mean, literally, what did you notice from those two numbers? All right. You got to say it as a sentence. The measures of opposite angles in opposite angles of a cyclic quadrilateral. I'm trying to restate this. Is, fill in the blank. Haha, there you go. The measures of opposite angles of a cyclic quadrilateral is, say that, and you've got it. Is an isosceles trapezoid a cyclic quadrilateral? I mean, if you think about it, you can go back to page, where was it? It was page 222. Page 222. Can you put these four corners on a circle? Turns out you can. And because you can, yes. In an isosceles trapezoid, the corners can lie on the edge of a circle. You can also add opposite angles. Yes. Add opposite angles. They add to, I'm not going to give you the number. It's the same thing all the way through. But because they add to that, that makes isosceles trapezoids. Makes isosceles trapezoids cyclic. Okay, you need to fill in the question marks. I'm not going to do that for you. You should probably already see the math. And thank you for watching this video. Moving forward, that's it for this lesson. Stick around for lesson 3. Make sure you get your homework done and ask me for help along the way. Thanks for watching. Bye. This button.